Hello and welcome to Root Causes, the PKI and Security podcast where a pair of industry veterans talk about all matters digital certificates and PKI. I'm Tim Callan, Chief Experience Officer at Sectigo, and I'm here with Jason Sirocco, Senior Fellow at Sectigo. All right, so I feel like I'm going to be taken all the way back to high school, Jay, because you want to talk to me about proofs.
Yeah, show your work. Divide this number by this number and show me your work. I remember those days too.
Let's talk about proofs.
All right. So all of a sudden, formal proofs, which been around forever, but they could become really important when we're trying to accelerate our trust in cryptographic algorithms.
Okay.
During these Toronto sessions, we talked about things such as diversity in cryptographic algorithms and different math. And how do we know any of this stuff is trustworthy? Yeah. Right? How do we know it's secure?
Right. So let's start with, how do we know RSA is trustworthy?
And I'll tell you what that comes down to is, I think that
nobody's broken it yet, and a lot of people have tried.
Nobody's broken it yet,
right?
And it's taken a long time, and it still holds, but it could be deprecated tomorrow morning.
Right. Yep.
Right.
Yep.
And it would be deprecated by really, really clever math. Quadratic sieve is a type of math where it's basically pattern finding. You might recall my little explanation about pattern finding in Shor's algorithm podcast. So, all right, formal proofs. I want to talk about not just the formal proofs themselves. That's awfully dry. That's dry like the Nevada desert. Let's put some... Where's the juiciness in that story right now? Leonardo de Mura, and I could be pronouncing his name wrong, have not personally met the man. I believe he's out of England, worked originally in Microsoft research and came up with an idea, I think around 2013, of, hey, can we codify formal proofs?
Okay.
So in other words, not just computer-assisted formal proofs, but can we write a formal proof, turn it into a language like C++?
Okay.
Right. So Fermat's theorem. Correct me if I'm wrong, world. I'm not looking at notes. I'm doing this off the cuff. I think Fermat's theorem was written up in about 100 pages of paper. And that's Fermat's theorem. And you really have to understand the symbology of the math, to prove it out. In other words, good old-fashioned high school show your work is what this person did in order to be able to prove Fermat's theorem. Okay, so there's the theory and there's the proof for it that's written out. But what happens if you could proof as code? Would that help us to utilize AI in proofing? In other words, can computer-assisted proofs, in other words, iterating the kicking of the can?
Sure. Right. You could see that being a very interesting application of AI, right? Where you let it kind of give you candidates of proofs, and then those would still be vetted by humans to make sure we agree, but it might get us to places that would be really hard to get to on our own.
100%. And AI, I'm just throwing out as a, hey, why not? It's a buzz term.
Sure.
But we can also, through good old-fashioned classic ways of doing things, just accelerate the iteration of finding what's the scenario that would unravel this cryptographic algorithm. And I would say that with these kinds of new computer-assisted means, codifying the proofs, there couldn't be a more important time than now to start really putting the foot to the gas pedal of these kinds of innovations, because we don't have the trust yet in these post-quantum cryptographic algorithms. Lattice has a lot of promise, but you've heard yourself, Tim, the amount of geez, we don't want to put all the eggs in that basket.
Yeah.
And the reason is because we don't have the kind of trust in it that we do with RSA or even ECC. What happens if we could write a true formal proof for it?
Right. And a true formal proof, like I understand the principle here. The principle is true formal proof is you do something mathematically that proves in a way that's indisputable by anybody who looks at it that you basically can't circumvent or break this cryptographic algorithm. And maybe this is a naive question, but isn't that proof itself based on a set of assumptions and a framework? And if someone could have an idea that is outside those assumptions and framework, doesn't that mean that the proof didn't deal with that?
Well, let's talk about ECC.
Okay.
And the answer is yes in that case. ECC as a math, right? Solving for points on that elliptic curve.
Right.
Well, it turns out that if you chose the wrong parameters for the curve, everything fell apart.
Okay.
But then that was figured out, right? And there was a 3-letter agency that was involved in that shenanigans, right? Let's not talk about that. I don't want to get into controversial stuff in this podcast. But there you go. And so therefore, yes. But then therefore you could put an additional set of proofs on, well, here are the acceptable parameters and other assumptions.
Right.
So therefore for any...
But then that assumes that's fine. But then it all hinges on your assumptions being right. And if your assumptions are not right, if your assumptions are, let's say, too narrow, then that's a problem.
Right. However, words aren't used lightly in math. And so when we say proof, we mean proof. It's not like, let's go out in the street and look at some marketing and when they say they prove something. It's not the same kind of proof, where it's loosey-goosey proof. You're right in saying that. I get what you're saying about part of the academic community, back when I was part of it. Being upfront about your assumptions was what made you a good scientist.
Sure.
The better you were about declaring your assumptions, the better you were as a scientist. And those are the people who were truly respected.
Yeah.
And so therefore, let's talk about Fermat's last theorem as an example. Not a lot of assumptions going on. Like the equation that was written out is right there in front of you. And is it true or is it not true is now understood by Fermat's last theorem proof as being, no, this is proven. And so when we talk about cryptographic algorithms, there are a finite number of assumptions. So it's not like, oops, we missed an assumption. So if we were in a type of environment with ECC where, oops, we missed an assumption about, parameters, then yeah, that situation did in fact occur, but that was just because I think things were being sloppy. Now that's controversial, okay? I don't really want to get into that so much, but I think to answer your question, is lattice geometry appropriate? I think that a formal proof could probably be written for that. It is a certain number of parameters around the way that you choose specific geometries. Is this appropriate for a post-quantum algorithm? And so therefore, just in asking that question lays out some of the assumptions, right? Therefore, you can write a proof about that. So would we find other assumptions or other problems that would help to unravel after that? I think this is what the exercise really needs to be. But this is really all about talking about how we can utilize the tools we have in order to be able to kick the can harder and faster.
So is that being done today?
Computer-assisted proofs, I think, are used all over the place. And I can't speak for the teams who are coming up with these cryptographic algorithms, but if you look at some of the paperwork, the research papers that are around this, yeah, you can tell there's definitely some classical proofs being done to help to make people understand pieces of the story. But I think complete proof sets that are codified are something that we're probably a ways away from getting. But I definitely think there's some exciting innovation in the tool sets in order to be able to do that. That's really what this is all about.
All right, cool. All right, thank you, Jay.
Thank you, Tim.
This has been Rukazis.